Hello everyone, welcome to the lecture series on computer architecture and organization. This is our fourth lecture under Unit 3, the processor. This is how we built a simple implementation using the data path and control lines. If you see here, this data path, we can add the control unit. The control unit must be able to take inputs and generate a control signal for each state element, the selector control for each multiplexer, and the ALU control. The ALU control is different in a number of ways, and it will be useful to design it first before we design the rest of the unit. So if we see here, this is the ALU control lines and its function according to the 4 bits. So depending on the instruction class, the ALU will need to perform one of these first 5 functions. NOR is needed for other parts of the MIPS instruction set not found in the subset we are implementing. For load word and store word instructions, we use the ALU to compute the memory address by addition. For the OR type instruction, the ALU needs to perform one of the 5 actions depending on the value of the 6-bit function field in the lower order bits of the instruction. For branch equal, the ALU must perform a subtraction. We can generate this 4-bit ALU control unit. We can generate the 4-bit ALU control input using a small control unit that has as inputs the function field of the instruction and a 2-bit control field which we call ALUOP. This is shown in the second column of this tabulation. This ALUOP indicates whether the operation to be performed should be add, that is for load and store instruction, subtract 0, 1 for the branch equal instruction, or determined by the operation encoded in the function field. The output of the ALU control unit is a 4-bit signal that directly controls the ALU by generating one of the 4-bit combinations that are shown in the previous slide. And this figure shows how to set the ALU control inputs based on the 2-bit ALU OP control and the 6-bit function field. The ALU OP bits are generated from the main control unit. See, this style of using this multiple levels of coding, that is the main control unit generates the ALU OP bits which then are used as input to the ALU control that generates the actual signals to control the ALU unit is a common implementation technique. Using multiple levels of control can reduce the size of the main control unit. Using several smaller control units may also potentially increase the speed of the control unit. Such optimizations are very important since the speed of the control unit is often critical to clock cycle time. If you see here, the first point, there are several ways to implement the mapping from the 2-bit ALU OP field and the 6-bit function field to the 4 ALU operation control bits. Because only a small number of the 64 possible values of the function field are of interest, and the function field is used only when the ALU OP bits equal 1, 0, we can use a simple piece or a small piece of logic that recognizes the subset of possible values and causes the correct setting of the ALU control bits. If you see here, this is the truth table for the 4 ALU control bits. The 4-bit ALU control is set based on the 2 input fields. Here it is the truth table entries for which the ALU control must have a specific value. So why we have shown this ALU control with a specific value means the truth table is very large, that is 2 power 8 is equal to 256 entries, and we don't care about the value of the ALU control for many of these input combinations. And in many instances, we do not care about the values of some of the inputs, and because we wish to keep the tables compact, we also include don't care terms. A don't care term in this truth table that is represented by into mark indicates that the output does not depend on the value of the input corresponding to that column. For example, when the ALU OP bits are 00, as in the first row of this column, we always say the ALU control to 0010 independent of the function code. In this case, the function code inputs will be don't cares in this line of the truth table. Once the truth table has been constructed, it can be optimized and then turned into gates. This process is completely mechanical. So this is about designing the main control unit. So we have learned how to design this ALU control unit that uses the function code and a 2-bit signal as its control inputs. Now we can return to looking at the rest of the control. So to start this process, we should identify the fields of the instruction and the control lines that are needed for the data path. To understand how to connect the instructions of the fields to the data path, it is very important to review the formats of the instruction class. There are several major observations about this instruction format that we will rely on. The opcode, that is the OP field, is called the opcode. It is always contained in the bits 31 to 26. The two registers to be read are always specified by RS and RT fields at the positions 25 to 21 and 20 to 16. This is true for the R-type instructions branch equal and store. The base register for load and store is always RS, that is 25 to 21. The 16-bit offset for branch equal and load store is always in positions 0 to 15. The destination register is in one of the two places. For a load, it is in bit positions 20 to 16, while for an R-type instruction, it is in bit positions 15 to 11. Thus, we will need to add a multiplexer to select which field of the instruction is used to indicate the register number to be written. This data path is figured with all the necessary multiplexers and all control lines that are identified. The given figure shows the 7 single-bit control lines plus the 2-bit ALU OP control signals. We have already defined how the ALU OP control signal works, and it is useful to define what the 7 other control signals do informally before we determine how to set these control signals during instruction execution. So if you see here, this tabulation gives the function of these 7 control lines. Coming back to this data path, the control unit can set all but one of the control signals based solely on the opcode field of the instruction. If you see here, the PZSRC control line is the exception. That control line should be asserted if the instruction is branch on equal and the 0 output of the ALU, which is used for equality comparison, is asserted. To generate the PZSRC signal, we will need to add together a signal from the control unit, which we call branch, with a 0 signal out of the arithmetic logic unit. These 9 control signals, that is 7 that is already in the tabulation along with the 2 for ALU OP, can now be set on the basis of 6 input signals to the control unit, which are the opcode bits 31 to 26. So that's all about this lecture. Thank you.